Welcome to another exciting education video brought to you by Chrysolite Tutors. We master calculations, excel in science, and learn anytime. So we're looking at a series of JAMB past questions. We'll be focusing on physics, and we'll look at gas laws and the calculations related to gas laws. So number one here, I have a gas at pressure P1 is 100 kilopascals. It occupies V1 at 500 cm cube. If the pressure increases to P2 is equals to 250 kilopascal at constant temperature, what is the new volume? Assume ideal gas behavior. Okay, so this is actually a relationship between pressure and volume at a constant temperature, and this is known as Boyle's law. Boyle's law. So Boyle's law says for a fixed amount of gas, P1 V1 is equals to P2 V2 at constant temperature. So the first thing you do is to write out your parameters. P1 is 100 kilopascal. It's here in the question. V1 is 500 cm cube. Is here in the question. And P2 is 250 kilopascal. It's also here in the question. So we have V2 left to look for. V2 is not given. So that's our priority. Okay, so by the time you plug everything into the equation, you have your P1 as 100, your V1 as 500, your P2 as 250, and your V2 unknown. So you can make V2 with a formula where you solve for V2, and the final answer you get is 200 cm cube. So the next question is Charles law. Temperature and volume change. Okay, so at constant pressure, that's what Charles law is. So the question goes like this. A gas occupies 2.0 liters. So this is the volume, 2.0 liters. So this is the volume. Let's say V1. Volume V1, right? At 27 degrees C. So this is initial temperature T1. Okay. If its temperature is raised to this 127 C degree, so this is T2. The temperature is T2 here, T2 at constant pressure. What is the new volume using Kelvin scale in gas law? So this is Charles law because we're told that the pressure is kept constant. So we're going to write out Charles law. It states that V1 over T1 is equals to V2 over T2. Okay. Now, the first thing we'll do is to convert all temperatures to Kelvin. So for T1, you have 27 degree, add to 273 to get this 300 Kelvin. Add for T2, it is 127 degree in the question, centigrade. You add to 273 Kelvin to get 400 Kelvin. Having converted temperatures to Kelvin, we'll plug it into the formula. So this is V1 over T1 and V2 over T2. So we can make V2 to be the formula. By the time we cross multiply, you get 800 divided by 300 is equals to 2.6 liters. 2.6 liters is the answer. Okay, so the third question is just to show us temperature conversion. To convert 50 degrees C to Kelvin, useful for all gas calculation. So just convert, add your degree C to 273, you get 323 Kelvin. All right. So the fourth one is talking about thermal expansion and linear expansivity. So linear expansivity is given as this. Linear expansivity is equals to change in length per unit length per degree rise in temperature. So the change in length is delta L, and this is L1 initial length, and this is delta T, change in temperature. So the question here is a tape is calibrated at 27 degrees C. So this is the initial temperature, 27 degrees C. Then it now say at 10 degrees C, it reads a block as 30 cm. So this is the initial length, initial length. What is the actual length of the block if the steel is coefficient of expansion is this? This is the coefficient of expansion, 1.2 times 10 raised to the power minus 5. Okay, so the formula is gotten from what I defined here. So this is actually the original length is O, original length, and this is the final length. Final length is what we are looking for, the actual length what we are looking for. So you have 1 plus alpha. Alpha is the coefficient of expansion, and delta T is the change in temperature. So it's actually gotten from this formula. Let me let me. This is the definition by first principle of this. So we are looking for L2, right? So if I want to make L2 subject of formula, L2 subject of formula, what I will do is to multiply this and this. So I'll say theta L1 then delta T, change in temperature, is equals to L2 minus L1. Okay, so here I will take L1 to this side. I will take L1 to this side. When L1 goes, it becomes L1 plus alpha. Alpha is linear expansivity. L1 again, then delta T. So is this component plus this component, right? That's what I have here. Is equals to L2. L2 is what I'm looking for. So I can see that L1 here and L1 here are common. So I say L1 outside, open bracket. Then what is left in this first term is 1 plus, then what is left in the second term is alpha delta T. Then I close the bracket. Is equals to L2. So this formula here is basically what I have written here, right? Okay, let me take this off. Let me take this off. So we are asked to look for the length, the actual length, and the formula is already, we have already made that one sort of formula. So I'm just going to plug in the values that we have, the values that we have. So, so in this case, calibration is at 20 degrees C, not the measurement temperature 10 degrees C, because tape contracts at lower temperature. Its marking are closer than standard. Okay, it's just so change in temperature. This one, delta T, is actually 10 minus 20. So 10 is the final one. 10 is the final one. So it's what is happening is contraction. Contraction. Uh, at higher temperature it expands, at lower temperature it contracts, right? So it is final temperature minus initial temperature to get minus 10. So this minus 10 is delta T, right? Is delta T. Minus 10 is delta T. So this minus 10 is for this one. So this one, alpha is already there. Alpha is already there. Okay, and then there's 1 and there's initial length. So I plug it in. So initial length here is 30, is initial length. Then 1 is also 1. Then alpha is actually the expansion, linear expansivity, and the delta T, we're writing it as minus 10. So we just solve and get final answer. All right. Okay. So for the ideal gas equation overview, let's look at a question here. It says find number of moles, that's 5 moles N of gas in a 6-liter container at 101 kilopascal and 27 degrees C. Take R as this. So R is 8.314 joules mole per Kelvin. So PV is equals to nRT. So this is the formula for ideal gas law. Uh, so this is where this P is pressure, V is volume, N is the number of moles, R is the universal gas constant, always given as 8.314, and T is the temperature in Kelvin. So this is the formula, yes. So we just in physics, the first thing you do is to understand the question. Second thing you do is to write down the formula. Third thing to do is to look for every parameter in the question and plug into the formula. So I'm going to be converting kilopascal to Pascal. pressure there is given as 101 kilopascal. To pascal is now 1,000, sorry, 101,000, because 1,000 pascal make 1 kilopascal. Okay, for volume, I have 6.0 liters. So convert it to meter cube. So 1,000 meters make 1 liter. So to convert it to meter cube, just divide 6.0 liter by 1,000, and I'll be getting 6.0 times 10 to the power minus 3. Okay? Yes. So for temperature, you convert 27 degrees C to Kelvin. Just add the 27 degrees C to 273. You get 300 Kelvin. So plug into the formula, and N will not be there because we don't have N, and that's what we're looking for actually. See, N is just looking different. So this one is pressure, this one is volume, this one is R, and this one is T, just like as I have it here, but N is missing. So we can make N with the formula. N will now be 0.243 moles. So note here that always convert temperature to Kelvin for gas law problems. Always. Okay. Then Boyle's law applies when T constant. Charles law when P is constant. Remember that. Boyle's law apply when T is constant. Charles law applies when P is constant. The ideal gas law, PV is equals to nRT, is used when PV and T changes. Okay, so we'll go on to the next slide. Ideal gas law solving temperature problems. So here we say we should calculate the temperature of an ideal gas at a pressure of 7.6 times 10 to the power 6 Newton per meter square, and the volume is 1.0 times 10 to the power minus 3 meter cube, containing 6 moles of gas. Again, this is ideal gas law. PV is equals to nRT. So we'll write the formula out and check the question and plug in the parameters. From the question, P is given as 7.6 times 10 to the power 6. Then V is given as 1.0 times 10 to the power minus 3 meter cube. And N is given as 6 moles. So we can get R. R is given, yes, R is a constant. So T can now be gotten. Temperature can now be gotten. But when you get your temperature will be in Kelvin. So, but in case if you are asked to convert to uh, Celsius, degrees Celsius, what you do is to subtract 273 from what you have here. This temperature will be giving us negative, but then your answer in Kelvin is still correct. Okay. So the next one is work done by an ideal gas. A gas at P is equals to 1.0 times 10 to the power 5 Newton meter square. This is the parameter. Expands isothermally. So note this term isothermally is a formula for it, from 0.6 meter cube to 1.2 meter cube. Calculate the work done by the gas. So formula for work done in this condition, isothermal condition, is W work is equals to P1 V1 ln V2 over V1. Okay, natural log. So already given V2 and V1. Okay, so write out the parameters again. Using Boyle's law, P1 V1 V2 P2 V2. So work done is this particular formula. So we're going to plug in the values there. What is P1? P1 is already given as 1.0 times 10 to the power minus 5. That's what I have here. Then V1 is given as 0.6. But the ratio between V1 and V2 and V1, this is V2 up here and this is V1 here. So if we get the natural log of this fraction, this 1.2 divided by 0.6 is 2. Okay, so already I'll be having link 2 here. That's why I have link 2 here. Okay, and I have this one, and the combination of this and this will give me this, right? So the answer should be 4.16 times 10 to the power 4 joules. The answer is in joules. So we are going to linear expansion, ratio and percent change question. So they have two. We have two metals, P and Q of length, LP and LQ. So two metals. So let me just do the metals like this. This is one metal. This one is called P, and the second one, this one is called Q. And the length, this length is the how long it is. So this one is LP, and this one is LQ. Okay, so the two of them are there, right? It's Q. Okay, so if the ratio of their linear expansion is uh, 2 to 3, so um, linear expansion, linear expansion, uh, change in length is equals to linear expansivity, initial length, change in temperature. This is it, right? So, uh, so that change in length for P will now be written as alpha length of P and change in temperature for P for P. But we're told that they have the same temperature difference. They have the same temperature difference. So this temperature difference now is that T. The same thing as for LQ. So this is LP, change in length, change in length for P and change in length for Q. So the same formula is here, but the length of the length is actually different. So there are two different lengths. So, but the temperature is the same. Temperature change is the same. So I'm writing this one formula for two different instances. For for the P, the P, it is taking this formula is coming from the general formula. Just that when you see L is LP, and the linear expansion is for P because P is a different material. So the expansivity, linear expansivity, is a constant there is for the material P, and the constant here is for material Q. So the only thing that is different, why these formulas are different, is that the L's in the formula, the L in the formula is for LP in P's cases, for in P's case, and LQ in Q case. And the expansivity, linear expansivity constant for uh, P is alpha P for P sake and alpha Q for Q sake. But the temperature change is the same. So I can remove it, I can cancel it out. Why? Because it is the same. So I cancel it out. That is why when you come here, we are not seeing temperature in this formula. It is here. It is here before. When it comes to this ratio of LP to QP, LQ, sorry, we will not have change in temperature. Why? Because it's the same thing. To cancel out. So this is what is left for the ratio. The ratio between expansivity of L to expansivity of Q. This is what is left. Okay, so by the time we plug in the values, we have that the ratio of linear expansion is 2 is to 3. So this part is 2 and this part is 3. That's why I'm having here as 2 over 3. This one is 2 over 3. And for this one, this part is 4 and this part is, sorry, this part is 3 and this part is 4. That's why I'm having 3 over 4. So by the time you do this, you get 2 over 4. And 2 over 4 will reduce to 1 over 2. So that's the answer. 1 to 2 is the ratio. Okay, so there's a concept known as the root mean square speed of gas molecules. So the root mean square is given as um, 3 ART over M, all square roots, where R is the universal gas constant, T is the temperature in Kelvin, and M is the molar mass. So the question says a standard pressure uh, and at this temperature. So T is already given as 293. This is converted, 20 is converted to 293. If you add 273 to 20, you get 293. Okay, so T is 293. The root mean square speed of helium atoms in a balloon close to what? Okay, so is close to what? So we're looking for the root mean square. Root mean square is VRMS. So this one is looking for this one. R is already a constant, 8.314, and M for helium is a constant. There's a given value for M. Okay, so we're trying to plug in the parameters. Again. T is 8.314. That is 8. R is 8.314. R is 8.314. R is 8.314, and T is 293 Kelvin, and M for helium is 4 times 10 to the power minus 3 kilogram per mole. Okay, it's supposed to be given in the question. It's a constant. It's a constant. Okay, please look for it. The question is supposed to be given as a constant, but it's not here in this my display. But in the question, it's supposed to be given the molar mass of a particular element we are considering. So this is the molar mass for helium. So what we just do simply is to plug in the formulas in the parameters in the formula. So this now becomes VRMS is equals to root of 3 is in the formula. Um, R is a universal constant, so is also the constant here given. K is the Kelvin for temperature. Is the temperature in Kelvin, and it's given. And M under here is the molar mass, is also given. So when you plug everything, we calculate, and we're getting 1.827 times 10 to the power 6. So by the time you do the the square root, you'll be seeing 1351 meter per second. So this is actually velocity approximately. Okay, so there's another question here. It's all about internal energy uh, change, monoatomic gas question. So this is telling us to calculate the change in internal energy of 3.00 moles of helium gas monoatomic when its temperature increases by 2 Kelvin. So this is the formula for monatomic gas. So this is the energy. U is energy. 3 over 2 is a constant. N is the number of moles. R is universal gas constant. And the T is temperature in Kelvin. So the moles is given in the question. The universal gas constant is a constant. Will also be given always 8.314, and the temperature is in Kelvin. So when we plug in the parameters, we'll be having 3 over 2, which is represented in the formula here, and the N number of mole is 3. So number of mole is 3. Universal gas constant R is 8.31, and the temperature in Kelvin is 2. So this is what will compute to give us this. By the time you compute this one, it is 3 times 3 is 9, 9 over 2 times 8.1 times 2. So the final answer will be giving us 75 joules. So as a key summary for what we have done so far, know that Boyle's law is P1 V1 is equals to P2 V2. Charles' law is V1 over T1 is equals to V2 over T2. So ideal gas equation for where the three are complete is PV is equals to nRT. So when do we use the three formulas? If you are given the question and you are told that you have the pressure and volume parameters, but they say that the temperature is constant or at constant temperature, that is Boyle's law. That is when you use P1 times V1 is equals to P2 times V2. Now, in the question, when you are given that there is volume, there is temperature, but at constant pressure, you'll be using Charles' law, where it states that V1 over T1 is equals to V2 over T2. Normally, they will give you three parameters remaining one, or then you start using mathematical your skills to or mathematics to get that one by either by way of plugging the equation and getting the subject formula and finding out the final answer. Also, but so generally, calculation in physics, all you have to do to understand the question first of all, write down the formula, then define the parameters, get what values, the parameters, what every letter in the formula stands for, what value are they assigned to in the question. Okay, so you solve. Then we'll also move ahead and we got the formula for work for isothermal cases where W is work in joules is equals to P1 V1 L ln V2 over T2 over V1. So for linear expansion, say it's the increase in length, the unit length, per degree rise in temperature, while the RMS speed is Vrms in meter seconds is equals to big square root 3 RT over M. And finally, in this session, we saw internal energy for monoatomic gas that U, this internal energy is equals to 3 over 2 NR then delta T. Okay, so we are going further to temperature thermometer scale conversion questions. There's a calibration question here. It says a thermometer X reads 20 degree X at ice point 0 degree and 120 degree X at steam point 100 degree C. What is the temperature on the scale X when the Celsius temperature is 40 degrees C? So this question is for conversion. There are there's a known standard already. I'll just illustrate it by trying to draw two thermometer tubes here. The first one, I will just draw this one. And this one is the one that is having the standard. The standard is calibrated in degrees Celsius. The lower limit is always 0 degrees C. You know that, and the upper limit is 100 degrees C. That is the temperature at which water boils, 100 degrees C. So this is the standard. This is the standard. But the second one is the one that we don't know much about. It's given as a calibration in degree X. This is degree C. Degree C is known. Degree X is we don't know it. We want to just deduce from the degree C what values are there correspondingly in the degree X. So for the degree X, the thermometer X reads 20 degree X at lower limits. So this 20 degree X here is the same thing as 0 degree C here, right? And 120 degree X as the steam point. The steam point is where the boiling happens. So 120 degree C. So the 120 degree C, sorry, the 120 degree X here is the same thing as the 100 degree C here. So, in your mathematics, you talk about proportion. By way of proportion, you can now deduce that if 0 here is equals to 20x here, and 100 degrees C here is equals to 120 degrees S here, what is so and so? So, we're now asked, what is the temperature on the S scale? On the S scale, temperature on the S scale, when the Celsius is 40 degrees C. So this is 40 degrees C Celsius. So we'll just use our simple proportion and say that from 40 to 0 is 40 minus 0. Then all over from 100 to 0 is equal to 100 minus 0. So this one is the Kelvin side is equals to, now the X side from X to 20 is X minus 20 all over from 120 to 220 again is 120 minus 20. So I can now know that I have everything value except for X. So this is something that's saying 40 over 100 is equals to X over, uh, X minus 20 over 100. So 120 minus 20 is 100 here. So I can now find what this means. I can cancel this 100 and this 100. So what I have here, let me continue this way. What I have here is uh, 40 uh, is equals to x minus 20. So I can now say um, minus 20 goes to this side. It becomes 40 plus 20 is equals to x. Therefore, x will be 60 degree x. So this is the value of this here. Okay. So I hope this clarifies. I can just show you how it is done here, 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 and here. All right. So the next one is area expansion. So area expansion, you recall from the slide where we talk about linear expansion, is change in length. That's linear expansion means the change in length per unit length per degree rise in temperature. So the same thing applies to area expansion. It says instead of having length, now say area, change in area per unit area per degree rise in temperature. So the question here says a square meter plate has a side of 0.2 meter at 30 degrees C. If heated to 80 degrees C, the coefficient of linear expansion is 2 times 10 raised to the power minus 5 degrees C. Find the increase in area. Find the increase in area. So first of all, change in temperature is given as 80 minus 30 is equals to 50 degrees C. Look at the temperature. One temperature here, one temperature here. So change in temperature is already given as 50 degrees C. Okay? And then initial area is given as uh, the side, one of the sides times raised to power 2, right? Because if it is square shape, the area will be length times length. That's length square. So from the length that is given here of one of the side, I can get the area. So I'm getting the area of the plate at initial point at when it is 30 degrees C, right? Then I can get the coefficient of area expansion because the relationship between area expansion and linear expansion is area expansion is equals to 2 linear expansion. Okay, that's the relationship. So I've gotten the from the area expansion already given. We're given linear expansion, sorry. From the linear expansion already given, I can get the area expansion. So I've gotten beta, right? Now, if I've gotten beta, I'll use the area expansion formula. Change in area is equals to beta. Beta is the coefficient of area expansion times area and times change in temperature. So this is coefficient of area expansion. This is area and this is change in temperature. Simply, you get your answer. So increase in area is 0.08 meter square. Okay, so we have combined gas law question. A gas occupies 300 cm cube at 27 degrees C, 100 kilopascal. Find the volume at 127 and this, right? Okay, so this is combined gas law. So this one now is P1 V1 is equal over T1 is equals to P2 V2 over T2, right? So you can write out the parameters. P1 here is what? P1 here is what? 100 kilopascal, kilo P. P2 is 200 kilopascal. P3 is not P3. V1 V1 is 300 cm cube. V2 is what we are looking for, right? Okay, so T1 is 27 degree C. Convert this to Kelvin. So just add 273. You get 300 Kelvin. And T2 is 127 degrees C. Again, convert to Kelvin, right? Convert to Kelvin. So I have everything already stated here. T1 converted to Kelvin, T2 converted to Kelvin. Ideal gas law, combined gas law written out. Plug in the values and get what get what the missing one is. What's the missing one? The missing one is V2, right? The missing one is V2. So we have in the stage where we are plugging in the formulas, we have done that. So we'll get V2 as what? As 200 cm cube. So this the pressure temperature law, they call that the Gay-Lussac law. So that one has to do with P1 over T1 is equal to P2 over T2. This is an equal sign here. All right. So you first of all write out your parameters, convert to Kelvin. Then this is the formula. You plug in the values, you cross multiply, and you get P2 as 66.7 kilopascal. Okay. So kinetic theory has to do with pressure from molecular motion. So it says the density of gas is 1.2 kilogram per meter cube, and the root mean square speed of its molecules is 500 meters seconds. Calculate the pressure exerted by the gas. So first of all, this formula is what is used to get the root mean square, the pressure exerted. Where P is pressure, 1/3 is just a number, rho is called density, and VRMS is the root mean square. So what are the parameters we are given here? We are given the density of the gas, rho, as 1.2 kilogram per meter cube, and we are given RMS value as 500 meter square. So these two values are given, we just plug them in and we'll get our answer. All right. The answer is 100,000 pascals. Okay, so now the note that we're taking away from here is that you always convert degree C to Kelvin. Always, don't forget that. Area expansion is two linear expansion. See, area expansion, area coefficient of expansion. Area coefficient of expansion is equals to 2 times linear coefficient of expansion. Volume coefficient of expansion is 3 times linear coefficient of expansion. So combined gas law handles change in P, V, and T. So if P, V, and T are changing at the same time, you have the combined gas law. RMS questions usually require squaring speed, and density must be in kilogram per meter cube. So I hope this video has been informative for you. I'd like to thank you for viewing. Please subscribe to our channel and invite your friends to come and watch what we are doing. Thank you.